So you have the pleasure to get me for the chapter 2 for 3 hours in a row. Today 1 hour, 50 minutes, and tomorrow we'll have 2 lectures in a row. So we'll go through all the chapter 2. So I have a little bit some announcement today. So Yoni told me to say some, what he told to me. Yes, okay. So when you have some technical question, it's very hard to apply in math and in machine learning technical question by email. So it's good to go to through the consultation hours. So I suggest you, if you have some technical question, go to the consultation hours. For example, Yoni has a consultation hours just after our lecture. Make sense? And if you have some question, you also will advise you to put on Canvas on the forum, and so all the students can help. And after 24 hours, if we don't have any good answer from your mates, we will answer to on the forum. Okay. Okay, so let's start. Can you see well my slides for today? Yep. Okay. So we try to use also my pencil. So is chapter 2. Today the plan is, okay, the rough plan. I try to do this, but okay, I break the lecture 10 minutes, 20 minutes, 20 minutes. Please raise your hand, ask some question, interact. I don't want to do to speak to myself for 50 minutes. So we will, this lecture is one which is a more statistics lecture, I would say. And after we'll go really in machine learning and deep learning. So today I will try to do the connection between the point of view from a statistician point of view and the machine learning point of view. Okay, and we do the connection. So we start slowly, and after we increase the pace, and it will be harder and harder. But today it will be normally quite easy. And you have different backgrounds, so stop me if something is not clear. Okay, so I just put here some two definition on the machine learning, which is has been the first. It was in 1959 by Samuel Muller. So you can read this definition, but which I like is the one from Tom Mitchell, which is say that the machine learning is a computer program is said to learn from experience E with respect to some class of task T and performance measure P if its performance in task T as measured by P improve with experience E. So this definition summarizes well, I think, the machine learning. And what I like to also is to put these pictures with this summary of the machine learning point of view. This picture is still from Andrew Ng. So for those who don't know Andrew Ng, is well known in deep learning, and he gives some lectures in Stanford, and now he's doing a lot of lectures on YouTube. So I suggest you to watch his video, and he has also a course on machine learning and deep learning in Coursera. So who knows Andrew Ng? Some of you? Yep. Okay. Oh, I have a question on assignment 1. Okay. I will reply to assignment 1 after Jade, okay? When we do a kind of break. Remind me. So this picture, so summarize a little bit the process. So you have some training set, some data, and you will use an algorithm which will learn from the training set and to build a model. And in machine learning, we will have this this fancy word with the hypothesis, which is nothing related to a hypothesis test, but it was like uh, just to specify the model. So, and after, when you have some new data, you use your model to predict, to have a prediction or a classification. Okay. So you have seen this yesterday with Yoni. So it's summary. So if I summarize what is the supervised learning, we try to estimate a function f, which link our outcome y with some features x. So, and this function is unknown, and this link is unknown, and you can have some kind of error or noise. So today my notation will be, we have some data which will have m data points, okay? 1 until m. Sometimes you use n for the sample size, but I will try to be consistent and talk with m for our data. So why we do this? So why we want to estimate f? Mainly to do some prediction. So when we have built our algorithm and we estimate our model, we can have an estimate of the unknown function f, which I call f hat. And based on this, I can predict a new outcome based on a new input x, which have not been used to train my model. This is the important part. But we can also use this process to do some inference. So in statistics, inference is well known. So it's in the way to understand the relation between the input and the output. So machine learning most of the time is kind of black box, but we will see that we can be able also to understand which input are the most useful to predict the outcome and what is the link and the relation between the outcome and the input and the features. And this is useful for decision making, but also to construct a better model. So in supervised learning, we have two tasks mainly. We have the regression task and the classification task. Yesterday, Yoni talked about the regression task with an example to predict in marketing the housing price, which is Y, our outcome, a quantitative variable. And I put another example with a climate model where we want to predict the increase in global temperature. And the classification task, we will work today with a qualitative variable, which is a binary variable for diagnosis cancer, and we will use this example. I put this on the chapter 2, and you can use this to do some filtering of the spam. So you have a good email or spam. And in image classification, we have worked with the MNIST data, or we want to classify some image, which is some digits. So regression task, classification task. Okay, so now we will talk more. So maybe I will ask a question. Is everybody is comfortable with the linear case, the regression model? Or some people have never seen the regression model? It's fine, but maybe not. Can I have some yes, no? Okay, so mainly yes, but some never seen, some recently, some a while, and so on. So I will go back on the regression linear model, but you have all the information on the course note. So the way is we have your outcome y, and you want to link this to predict this outcome, the quantitative variable, by some features. And features and statistics we call in covariates, some explanatory variable. So you want to have your x, some information, and you want to link to y. And the way to do this, the simple model, is to do some linear combination. So the linear combination is just the beta. So it's here. So in this linear combination, it's just you have beta 1 multiplied by x1, the first characteristic, plus beta 2 multiplied by x2, and so on, plus beta d multiplied by xd. So x is your information, explanatory variable, try to use to predict y or to explain y. Okay? And in statistic, beta is called the parameters, and in machine learning field is called the weights, because it gives me a weight on each information of each covariance. And beta 0 here is statistic is called the intercept, and in machine learning field is more called the bias. Okay, so each parameter is related, or weight is related to each features, if each characteristic of your information. So now you assume that this is a true link on x and y, and you want to estimate your weight, your beta. So to do this, there are two ways to do this, is to construct a loss function, and in statistics, we mainly use the likelihood approach. So who has never seen the likelihood approach? Oh, don't know what is the likelihood? Yes, no, yes, no. No, perfect. So today you will see, you will get it. Here does it, okay. So we'll come back on the likelihood also on this one. But we will start by using a loss function. So we try to estimate to get our model, and so we try to get f hat x the closest to y. Okay, so we need to evaluate if our prediction is good, so it's close to y. So to do this, we construct a loss function, and the most natural close function in the linear case is the square loss. So the square loss for an input is just the difference of the outcome and the prediction. And you take the square, and this is your loss function for one data point, one sample. Okay? So I just put some information that mainly this is related to the mean square error, and I will explain what is the mean square error, because you will do the loss function for all your data points. So now, if I consider that this was the loss function for just one observation, and now I have m observation. Okay, so keep in mind of the data that y is the outcome, x is the information for each observation, for each sample, and x is something with d features. Okay, is in RD. Make sense? And I have m data point. All clear for this? For the data? Okay, the data is okay. So now I need to compute my loss function for each samples, for the m samples. So I just do a sum of my loss function. Make sense? And I take the mean. So this is, I call this g of b, beta, because it depends on beta. And this is my cost function. So what I want is the cost function high or low? Somebody will me like this. Yes, low. So we want a cost function low because we want to have a loss low. So to get, so if I go on the, oh, next lecture, not the next lecture, come on. So wait for this. Oh, coming here. Yes, the loss function is here. And now you want to, okay, and where is it? Where I am? Oh, I am. Sorry. I'm here. I'm here. And so now if I develop this, I got, which is called is the least square. In fact, here, this is my loss function. And now I want to find this loss function is a value in R. This belongs to R, but is depending of beta. So I have a function is depending of beta, which is a vector of beta of dimension. What is the dimension of my beta? I put RD, okay, but I will move the intercept. So now, how to have this estimate? How you can do? What you do to get beta? You want to have the loss function the smallest as possible. So how to get it? Differentiate with beta. Yes, okay, optimize. Okay, so we will do this var, we know that var an analytic solution. So this is, oh, to do now, derivative. Okay, so let's do it. You have 2 minutes to do it. Take the minimum. Go it. Not, okay, Jade is a good point. We can do it with the steepest descent, with the gradient descent, and we will do it later with the gradient descent. But here we will do it analytically. We will take our pen and we'll do it the math. Just, it's like a nice end of the afternoon. You may be tired, but do it. Is in 3-4 lines is done. Okay, I'll let you 2 minutes. Try it. I will try to do it also. Okay, solution is here. I don't have the solution. We try to do it. So my cost function, I say, I don't know, I don't remember. Was this, it was 1 divided by m y minus x beta transpose multiplied by y minus x beta. So first step, we develop this. So if I do this, is 1 minus m y transpose y minus y transpose x beta. I'm sure I will do some error. Huh? Oh, okay, first error. Come on. Okay. Yep. First error was there. So what? Where I am? Yep. Maybe you're faster than me. Okay, I develop, and now what I have to do? Okay, oh my God, very fast. X transpose X minus 1, X transpose Y. Yes, but you know by heart this, maybe. So the step, and after you derive this, you differentiate in respect to beta. And so this, you don't care. And after you will have this one, you can rewrite because it 1 minus t x transpose y because it is a scalar, so you can take the transposed. Okay, so you have this term is minus 2 beta transpose x transpose y, and when you take the derivative on this, you will have so minus 2x transpose y, and this, if you take the derivative, differentiate in comparison to beta is a quadratic term, so it will be plus 2x transpose x beta. Make sense? And so now I did the differentiation of this. So now I need to be equal to 0. So I end up to, why this is here? Okay, here. I got that to x transpose y x transpose x beta, and this is called the normal equation. Are you lost? Not lost? And if x transpose x is invertible, you got that beta equal x transpose x inverse x transpose y. Okay, so one of the students say, oh, we can do an optimization. Yes, we can do an optimization, but in this case, you have an analytic solution. Okay, so I'll keep going, and if you have some trouble of this, we can come back on the consultation hours. Okay? Any question on this? I don't see any question. I did an error, maybe not an error. Okay, that's a little bit messy, but it's okay. Okay, I keep going. Likelihood approach. So the likelihood approach is another method of an estimation method, which is quite useful and handy for in statistics. So I just give you some reminder for IID samples. So if I have an IID samples, everybody know what is IID? If somebody can tell me what is IID?
Identical and independent. So identical, distributed, and independent.
Yes, thanks. I hear a voice, so you can talk. It's good. Independent, analytically distributed. Yes, so is that each random variable have the same distribution and they are all independent. Okay. So for example, if I have some a vector of random variable y1 until yn, the likelihood is just the information of your sample, and the information is given by the density, okay, the probability density, the PDF, probability density function, and is the product of all, because they are independent, the product of the n density function at point yi. Yes, exactly. Just to present, you can write the likelihood for more complex farmer work, but I just start with IID, just to explain, remind what is the likelihood. So the likelihood in the IID case is just the product of the probability density function of each variable. Okay. So, and just another example for those who doesn't know the likelihood, and I just why my example, which my model is say, okay, my random variable come from a normal distribution with expectation mu and the variance sigma square. In this case, our parameters are mu and sigma square. So the likelihood, which is a function of the parameter given from the sample y, and just the product of the density. You can see the product of the density there. So this is the likelihood for the normal cases. Any question on this? Okay, and now So this was a reminder. I think you have an exercise again. No? Okay, no, I finished. So the likelihood approach is to find, in this case, our parameter, which are the expectation in the variance, in my example, which maximize the likelihood. Before, we wanted to have the loss function the smallest as possible. Now we want to maximize the likelihood, because the likelihood is, you can see that is the probability to have observed this data given a specific model. So we want to find the parameter which give us the more likely to get this data. Make sense? So we want to maximize the likelihood, the probability to observe this data under the assumption of the model. So if I want to estimate theta, which is mu and sigma squared based on our observation y1 until yn, I need to, again, to differentiate the likelihood. And for convenience, as we have a product, we take the log likelihood. So in fact, the maximum likelihood approach is to take the log likelihood and after to do the differentiation in respect to the parameter and do the equation equal to 0. So this is the traditional way to do the maximum likelihood approach. So for the linear model, we have used before, if we put an assumption that our noise are IID with an expectation 0 and sigma square and a variance sigma square, this is our linear model. We can derive an estimator of beta based on the maximum likelihood. So this is a second exercise to do it. And this, I will let you to do it. I will not do now, but I'll let you to do this exercise. It's good to do it, just to see. And you will get the same estimator that we found with using the loss function and the square loss. In this case, it gives the same estimator. So try to do it, and you will get, normally you will get for beta hat, x transpose x, x transpose y. So this is a solution, but try to do it as an exercise, as a homework, okay? Okay, the solution, I don't have the solution yet, so you have to do it. Okay, and this was in the statistical point of view, but now as a neural network, in fact, we have just done our first neural network. So a neural network is a non-linear, it helps us to build some non-linear link between y and the features x with its function. Oh my God, sorry. Here. Yep. This with f. So we try to learn f, and just with the linear model, we have just built a linear link. Yes, the solution could going to be updated if you work on it. Yes, of course. So I represent my linear model like a shallow neural network. In fact, in this shallow neural network, we have just one neuron here. You can see here, which represent with a sigma, and we have our D features, and I put the one. Why I put a 1 here? Why I put the 1? Bias, yes, the bias. Okay, and each and after you have the beta, each arrow link with the weight in the machine learning, but in our linear model is a beta. Okay, and you can see that this neuron you have in sigma. What should we call here? Sigma here. in the neural network? If you read what is it is sigma? It's not related to the noise. Yes, it's the activation function. So in fact, this neural network, we have y. You have this beta transpose x give you the linear link, and to this linear link, you applied a activation function. And in the case on our linear model, the activation function is just the identity function. So it makes you something linear. But you will see that if we want a link, a non-linear link, you can apply an activation function which is non-linear. So it's just to tell you that, in fact, this linear model is just a shallow neural network with just one neuron and an activation function, which is the identity. Okay, keep going. So the most popular activation function is the sigmoid and the relu. What is stand relu? Somebody can write what is what's the meaning of relu? Both are non-linear. Rectified linear unit. Yes, we read. Rectified linear unit. Okay, question. Jade say, I don't understand why the activation is the identity function. Okay, so I come back here. I want to show that the linear model, remember that the linear model is y equal beta 0 plus beta 1 x1 plus beta 2 x2 plus plus beta d xd. Okay, so the link between y and x is linear, is x transpose x. X transpose, sorry. X transpose, you can write like this in the way, beta transpose x. Okay, Jade? And now, as this is arrive in this neuron, I don't need to apply a nonlinear transformation because I want something linear. So if I use the, yep, she got it. You got it? Okay, good. Okay, but later we do something nonlinear. So the nonlinear, the sigmoid, so it go from R to give you an output between 0 and 1. So this is between 0 and 1, okay? And the difference with the relu is that it gives you non-activation if your X is negative, and if it's positive, it gives you identity, okay? Something linear. So we see later the use of these two activation function and so more. So now, if I want to construct my more general neural network, how is working? You have your input, you have an hidden unit with an activation function, A1, and this give you the output, the prediction. Make sense? So first, you have the first equation. The activation function A1 is just take any activation function, which could be a sigmoid of a relu, on the linear combination of the features and some weight. Okay? And this gives me a prediction. Everybody understand what is the beta 1, 2, and A1? In this, I can put the notation. Here is beta 1 for the neuron 1, and this is the second. Yep. And now this is with 1 unit, but I can add a second neuron. And I have here A2, and A2 is an activation function. Most of the time is the same, but it's not need to be the same, on a new linear combination. Oh. Okay? Clear or not? So in fact, the red arrows are some other weights. So you have another set of weight. And with this, you will get now your outcome, your output is a linear combination in the prediction of the two output from the activation of A1 and A2. So you have also a weight here, beta 1, 2, and here you have beta 2, 2. Yes, so sigma each time is an activation function of a new linear combination of the input with some weight. I reply to the question, Jade. And you can see that for y hat, I didn't put an activation function at the end because we try to do some prediction. So it's like an identity. Okay, and I can go further and doing until then to add some unit, and unit. And then my prediction will be the sum of a linear combination of all the output from my first hidden unit. So in my model, in my shallow neural network, where are the parameters? The parameters are each arrows, which are the weight. So this is a parameter, this is a parameter, this is a parameter, this is a parameter, all of this is a parameter. Yes, this is now a two-layer network. Does mean the layer of the NN. Sorry, I didn't get the question. What is a bracket?
Maybe they can just speak up.
Yes. Can you reply your question? Can you ask again?
No, it's me, Benoit. I'm saying, they can speak up if they have mic. Can
Yes.
ask the question directly.
I can see Sarat. Yes. Yes. Please ask a question if you have a question. I didn't get the question, Jiao. Yes, good point. 2 points here. In this case, I just simplify. I could have put here also a bias and put a bias. Yes, good point. It's just to simplify the pictures, but we can add a bias. Yep. Okay. Oh, example using R. Oh, okay. So I'm very sorry, and Sarat is here. I will just show you a very simple example by using R to show a neural network in action. And I think you get the slide too, or not really? You got this or not? It give you I will share another screen. Sorry. Share screen. Yes, yeah. Let me know if you see this HTML file? Well, yes. Okay. Did you get this on the website? This one? You should. Nobody? Can you check on the website very quickly? But I will put again after, okay? But it's not very important. So I just show you that by any software, you can run very quickly a shallow neural network. And here, just for example, I just use the package in R, which is called neural net. And if you click here, you have an article on the R journal. And I use the data from the well-known data, which is Boston data, which for to predict the housing price. Okay, so is the example he put on the first chapter. So I just split the data because keep in mind we see in the next lecture that you have to split your data by the training set and a test set. So the training set is used to build your model and to estimate your model. And after the test set is to evaluate your model. Let me know if something is not clear. I can check the chat because I can see some people. No worry about R. We don't use the R. It's just to show you what is going on. We don't look at the code. So just to tell you that this is a result of my linear model, which I can use a linear model, and I compute the MSE. But this is important to know what is the MSE. Everybody is comfortable with the MSE. If you can see the formula. What is MSE? Very, very quickly. Somebody talk to me. Talk. What is MSE? Mean square error, mean square error. Okay, so everybody know what is the MSE. So I compute the MSE here to see what is the MSE for my linear model. But it's a linear model, so the link between the X and the Y is linear. Maybe it could be helpful, but we will see that with a shallow neural network, maybe we can have a better MSE. So I compute the MSE on the test set here, 31. So I want to have MSE low. So I build a shallow neural network, and just, I don't want to say R is good, but this neural network helps us just to visualize what is going on. So what I have done here, I just run a shallow neural network with, I put in my function 3 neurons in my hidden layer. So this is my hidden layer. You can see my hidden layer. And I have in blue the bias for each neuron unit. Okay? So I have each unit, and you can see all the arrows are the weight which have been estimated. And after, we combine the output of each after each activation, and we combine, and you put a weight. I put a weight here. Remember, I forgot, and I got the prediction. Clear for everyone for the neural network, this first neural network? So just want to show that in R and quite fast, you can just very quickly, and I check the performance. And the performance, you can see my here is 19. So better on the test set. And I was thinking, okay, now we'll see later on the chapter 4. Now is like an art to build a neural network, because you can, maybe somebody can tell me, oh, how can I do better? Tell me if you have an intuition to do better than this. How can I do better? Any idea? More here, more here, more here, more here, more nodes. Yes. Feed is fresh fruit and veggies. Okay. Yes, wider network. Okay, so I try it. So first thing to do, try to add some more units in my first hidden layer. I put 8. Oh, okay, I put 8, and you can see it's 13. It's going down, so better in prediction. And some students tell me, okay, maybe I should add a layer, so wider. So I put one more. So I put the first 8 and after second 4. Okay, and but you can see how it's increased the number of weights. So parameter increase. So you have to keep in mind, okay, the data are more capacity to learn from the features to the outcome, but they are more complex. And is it better here? Yes, it still is it better? Okay, it was just the first example to play. Okay? Any question on this? So at the end, you should be comfortable to understand how to build, what is a neural network and the weight and so on. So it's a good question. All of this, we will talk about this, how to design a neural network. And is really depend, the question, it was, should we have less unit in the next layer? Is not, you can have the same. They don't have is really depending the situation, and you will see when you we deal with image and so on and so on. It's really depending the application. Okay. Okay, I come back to the slide. I cannot imagine it's 46. I'm sorry. I need the double. Yes, we'll talk about overfitting soon. Exactly. But the overfitting here is, as you can see, that it still doesn't not overfit here, the model, because my MSE decrease is on the test set. I compute the MSE, is a good point, on the test set. It's not on the training set. Okay? Okay, Will? Okay, I try to stop the sharing here. Stop sharing. Yes, good. Share again. Is here. Yes. Oh my God, not this one. Do you see my screen? What do you see? Yes. Oh. Okay. You see my slide or not really? It's not this one I want to see, to show. Okay. Share screen is not this one. Share screen, this one. Yes. I hope it will be okay. Yeah, good. Demo done. Okay. Now is, what time you have? Oh my God. Okay. So now we go to a regression in a binary outcome. So the binary outcome, now we have, when you have a binary outcome, in fact, you want to do some classification. So we move to the classification task. And just to show you that in the classification task, we will, in the statistical point of view, you will use a binary, you will use a logistic regression. And if you have read the chapter, the logistic regression is also a neural network with a specific activation function. So to do the logistic regression, I just ask some questions because I will not have time to go through all of this. Which activation function correspond to the logistic regression? So for a task, we want to classify a binary variable. I think I have a good response. Yes, so we will use the sigmoid function. And the sigmoid function, you will see the parallel with the logistic regression. But for the logistic regression, yes, and when we will use multi-classification task, we will use the softmax activation function. And I will ask another question. I will ask plenty of questions. Which loss function we use for binary classification problem? Will, can you explain to me why you say L1? What is L1 for you? Yes, so L1 norm, but L1 norm is, we don't use L1 norm for like a loss function. So I don't get this. The log likelihood or the cross entropy. Yes, you use the cross entropy and you will see the parallel that is similar as the log likelihood for binary. Okay, and why now? A question we will see tomorrow, but I prefer to ask the question before. Why we use the cross entropy and not the square loss? Do you have an idea? It was not in the slide and it was not on the chapter 2, so I tried to ask a question. My question is, for the linear case, we have used the square loss. And now, for the binary case, we use the cross entropy loss. And I ask why we use the cross entropy loss instead of the square loss. Do you have an idea? I want some precision, Kevin, about the poorly defined. Yes, you have some intuition. I like the cross entropy converge better. Why is the meaning that this converge better? So you will see tomorrow that, in fact, when you use the cross entropy with the sigmoid activation function, your optimization problem is a convex problem. And as is a convex problem, you have a minimum. But with the square loss, when you use square loss with the sigmoid, is not a convex problem. But we'll see tomorrow, and you will have an exercise to do this tomorrow because we talk about convexity also tomorrow. Okay. I don't know if I have time to go, it's 52. Oh, 52, we say 15 minutes, okay. So, just to let you know that this example, just to start, and your work for tomorrow will be, please, I know that you're tired, but just go through these slides, just to read these slides, okay? For tomorrow. And you have the slides tomorrow also. You will have now, Yoni put on the website the slides for tomorrow too.
Yoni already has put them on the website.
Yes.
Yeah.
So you have the link on the website for the slides for tomorrow, okay? Maybe we will not go through all the slides. So the good way to work on together is you have to read before, try to think about the slides, the material, and if you have some trouble to understand some stuff, you note, and tomorrow you ask some question, and I go on the part which is not clear to be more efficient. It makes sense? So you have to do, okay, the communication, you work first, and after, because I cannot go through all the material in details, okay? So I drive the lectures, but I prefer to go through some specific part which is unclear for you. It will be more efficient for everyone, okay? Make sense? And my recommendation and my suggestion at the end of the slide, I put a list of take-home message. So this list of take-home message, you can see, at the end of the lecture, you should be comfortable to write 1 or 2 sentences on each word. Is the meaning that, or to try to explain to a mate, or your girlfriend, your boyfriend, your mother, your father, what is this? In simple word, likelihood. What is the likelihood? What is the heuristic model? What is the sigmoid, ReLU, square loss, cross entropy, metric, softmax? So at this end of this lecture, you should be comfortable to understand all these concepts and to be able to explain to somebody else. When you manage to explain a concept to somebody else, is the meaning that you have understood the concept. You think is a goal you can have to achieve? Yep. Can I have a go? Can I have a question? Can somebody give me 2 sentences about the ReLU? I don't know the pronunciation of the ReLU, so somebody can pronounce ReLU and tell me what is ReLU. And we stop on this. Somebody tell me what is ReLU. Don't be shy. Nobody for the ReLU? Yes, everybody give me the definition. So all together you manage to get it. So ReLU, nobody tell me what is the meaning, the name, ReLU. Write it. I think with everyone we have the combination of the good sentence. Why is called ReLU? Yeah. Okay. We have all. Yes. So a summary ReLU is a rectified linear unit, is an activation function which take any value in R, and the domain definition is R, and is going to R2, and you get the definition. And it's true that now is a little bit the gold standard of activation function for the hidden layer, but it's never used on the output layer. So keep in mind that ReLU is never used on the output layer, but is used on the for hidden layer. Okay, any question?
Benoit, I have one announcement.
Yes.
So regarding questions and the discussions, try to use Canvas. There is a place where it's called discussions. You can post your questions so that other students can participate and we can participate and we can have an open discussion rather than sending emails to instructors. And also we have this consultation hours. So there also we can discuss questions. Okay.
Okay. Yes. So Jade, regarding your question, can you put your question on the canvas and we reply it? Okay, Jade?
Yeah, that's going to be beginning.
Sarat, tell me is a boss, okay? Okay, Jade, you copy paste your question and you put on canvas. So everybody has the question and we can reply to the question about the same.
Yeah.
Okay, so to clarify, yes, so you have the slide today. So I suggest that you go through this slide, this one, but I haven't managed to go down. And for the slides for tomorrow, don't go to the slides for tomorrow, but read the material which is online. Okay, because the slide is like sometimes there's some extension and some part I didn't put online. So read the chapter 2, which is online. Read the slide of today, and just tomorrow we have the slide for tomorrow. I think it's clear, Peter. Is it clear? Yes. Okay. If you don't have any question, it's 6. You have a nice consultation hour, so join Yoni. Oh, Yoni is here. I have also a consultation hour. Yes, Yoni is in consultation hour. Yoni. Okay, thanks everyone. I hope to see you again tomorrow. So tomorrow we have 2 hours, but promise tomorrow we do a break after 50 minutes. You cut, stop it. 50-minute break, up. We do a little bit some exercise, some push-up, up, and after we start again. Okay. So tomorrow, be ready to do some push-up during 10 minutes. Okay. Okay. See you tomorrow. Have a good evening. And you have some French. That's good. Merci bien. À demain. Bonne soirée. À demain. See ya. I stop. I stop. See you tomorrow. Bye-bye. Jade, don't forget to put on the canvas your question, okay? Bye-bye. Yes, oui, okay. Merci.